So at some point, the pacing algorithm is going to say, when the live heap hits this point here, I'm going to have to run. And its goal is to try to get this live heap back down. So it's going to set this goal, and it's also going to set a goal on how long it needs to get this done. Now, once the pacing algorithm says, okay, we're going to start our GC, a few things happen. I told you again that everything's about a cost and a trade-off. And in the very beginning of Go, really up until 1.5, we had a fully stop the world collector. What that meant is when the pacing algorithm said it's time to run, every Go routine was basically halted. The GC did its thing, and then the Go routines ran again. We have always asked the garbage collector to not have that type of long latency. Those types of latencies hurt. We want to reduce the latencies. The garbage collector today can run concurrently with our Go routines. This is good. There's still some stop the world time, but the idea is that during the bulk of the GC operation, our Go routines can continue to run as well. And this is what we've asked. And when we asked the garbage collecting engineers, can we do this? They said, I can reduce the latency, but you don't get this for free. You have to take a cost. And we were like, what is the cost? And they said, you have to take a performance hit of 25%. So what does that mean that when the garbage collector is running, we have to take a 25% performance hit? I mean, one way to equate it is if you've ever been driving and you've been in traffic and the traffic's just not moving and you start to take side roads just because you feel like if I can keep moving, no matter what, I'm doing better. And it's kind of the same thing. Now, we're going to talk about concurrency again later, but what you can think about right now is that for every core that you have identified when your Go program comes up, the Go scheduler can put Go routines against it. So if we had a 4-core machine, what you can think is all of the Go routines that we create get distributed across these 4 cores. The garbage collector also has a group of Go routines that perform the garbage collection work. So when the pacing algorithm says, okay, we have to start, and this is how long it should take, what it's going to do in this scenario, the 25% performance hit, is it's going to take 25% of all of our available CPU capacity for itself. In this scenario, we can imagine that it's taking an entire core to itself. That's not exactly how it happens. We'll learn more during concurrency, but it's a good mental model to have right now, which means that these 3 Go routines get distributed across these other cores, and now the GC Go routines, they get this one all for itself, 25%, the 1 out of the 4. Now those Go routines go ahead and they start doing their GC work. But here's something that's really interesting. The pacing algorithm is gathering statistics about how these Go routines are operating. It knows. It's calculating how long this is going to take so it can maintain a pace, so we can bring it back here. This is what we want. Every time the GC runs, we want that to be back here, and we want this to happen not so frequently. It would be nice if this happened maybe every 5 or 10 milliseconds as opposed to, let's say, every millisecond. But what if on one run, everything was good, and the garbage collector starts, and suddenly this Go routine right here, this one, starts to go crazy. It starts allocating more than it ever had before. The garbage collector starts to realize, oh my God, this Go routine is going to cause this to go over the top, which is going to cause really large latencies because now we have to resize the heap. If the garbage collector identifies this, what's really cool is the garbage collector basically puts this Go routine in timeout and says, you are no longer allowed to operate. And in fact, you come in here and you start to participate now in garbage collection as well. So the Go routines that are doing what they've normally done, they get to operate. The Go routines that go off the deep end, they start doing something else. They all get dragged into helping with GC because this cannot run forever. This has to at some point get done. So the pacing algorithm drives everything. And it's a really amazing algorithm. It really does a nice job at running at the right pace for what's happening in the software. But this diagram here that I'm showing you on the screen, what it kind of does is gives us a high-level view of what that GC work actually is. And so we could briefly, again, to have a visual of what that work is, kind of go through this. So at the very beginning of the GC, what has to happen is every go routine that's there running has to be told that the GC has started and has to be told to start using the write barrier. The write barrier is a little function that gets called now every time you're doing something to the heap. And that is going to cause a little bit of stop the world. It's going to be so minimal you're not even going to feel it because every go routine's got to be told, hey, write barrier's on, write barrier's on, write barrier's on, write barrier's on. Once that's done, now what happens is that the go routines for the garbage collector get to start doing their thing, and go routines here get to continue to run. So the first thing the go routines have to do is scan every stack to find pointers to values that are on the heap. We call these the root objects. And every pointer that every root value that we find in the heap, we can throw into some sort of queue. So again, just a high-level visual. We might have values that point to values, that point to values, and we're going to have stacks that have frames that point to these different things. So every stack has to be looked at. Now, every stack starts out as white, and as every stack is scanned to find pointers into the heap, we'll mark them black, and then what will happen is these root objects, we'll change them from white to gray. And then we're going to pull this out, we're going to look at what it points to, we're going to make this gray, this is going to go black, this is going to go black, this is going to go gray, this is going to go black. And we're going to go through every single stack, and we're going to then go through every single object, trying to mark everything black or white. Anything after this phase, mark phase 1 that's white, meant, hey, we didn't have a pointer to it from any given stack. I guess it's not in use anymore. Anything that's black means that it is in use, and it has to stay where it is. Now, prior to 1.8, we had this second phase called mark phase 2. This mark phase 2 had to stop the world completely again. And this is because these go routines, when they're running, their stacks are changing. And things are changing maybe on the heap as well. You see, if these things are just doing things on the heap, we can just paint that object black right away. We know it's in use at that point, we can do that. But we have to then go back through all of the stacks that were changed during the run. So when any one of these go routines start running again, their stack, which was painted black, goes back to gray. But we've got to stop the world to do this because we can't have any more changes until we rip through those stacks that have changed. Now, hopefully, prior to 1.8, not a lot of go routines actually got to run across these 3 cores because this happened so fast. So there isn't a large amount of work to do. When I was in using 1.8 or less, if I saw stop the world times that were a millisecond, I would be a little concerned, though I think the top end they would always report as about 10 milliseconds. What's so amazing is that in 1.8, they found a way of getting rid of mark phase 2 from the GC. In other words, they don't have to stop the world to rescan these gray stacks. Because of that, the GC times now are being reported as a top line of 100 microseconds. That's right, microseconds. I mean, the GC now is almost irrelevant to what we're doing. And if the GC becomes relevant, then we are really doing something wrong in terms of our allocations. I mean, we're putting pressure on the GC that is just way out of hand. And during profiling, I'll show you how we can look at these things and find ways to fix that to improve our software. So the GC engineers have just done an amazing job at getting the GC out of our way. But like I said, we have to be sympathetic with everything we touch. These are just tools. We have to continue to move forward now and learn about value semantics, learn about pointer semantics. When should we share something? When don't we have to share something, right? Again, optimizing for correctness, consistency, integrity, readability. all of these things coming together all the time. So moving forward, I may mention to you every once in a while, what's happening here through escape analysis? What is the cost of this? Is there an allocation? Is there not? I want you to start reading code. And reading code means that you can understand the impact that code has on the machine, on every function, on every program, on everything we do. And what we've just talked about in the last 3 lessons, type. Type is life. It tells us the cost of every value, the size and representation. User-defined structs, how we're going to leverage them for our data structures. And now how pointers work, sharing, escape analysis, these semantics. This forms the basis for our ability to read and write code, to understand the mechanics of this language, so later on we can do better at designing and architecting our software, not just for today, but for tomorrow.